Hi folks, welcome back to Physics with Captain Rod here. I'm making this video to help you out with Unit 4, homework number 3. We're going to chat about numbers 13 through 16. So 13 says, let's see, a student drops a couple of metallic objects into a steel container that holds some water. So, oh, whoops, there we go. All right, so like usual, I definitely recommend starting this with a picture. So I know we've got a steel container. It's got water in it. A couple more steel objects are going to be dropped into that container. And let's see what else it says about them. So some things that are given here, I'm noticing the mass of the steel is a given number. The mass of the water is a given number. Initial temperatures of both the steel and the water is given. Because the water is in the container, by the way, and the container will conduct, these will be at the same temperature. Let's see, and we end up at the same, let's see, one object is 224 gram cube of copper. With a mass that's given in the problem. The other one is well, there's a lot to this problem. An unknown chunk of aluminum that is initially at 5 degrees. Copper says, mine says 84 degrees, but yours might be different. All right, oops. So it looks like the water is relatively cool. I'm going to read this again. The water is 25 degrees centigrade. Copper's 84, the aluminum is 5. Okay, so once these get placed in the container, we're going to have heat transfers, and we're going to have heat transfer from the copper because the copper is relatively warm. The aluminum is relatively cool, so we're going to get heat transfer to the aluminum. And the idea here is that if we define our system like this, no energy is walking across that boundary, or at least we can assume such. It's reasonable to do so, which means the heat transfer for the water plus the heat transfer for the copper plus the heat transfer for the steel plus the heat transfer for the aluminum all have to add to 0. Now, every one of these is an MC delta T term. So you're going to have mass of the water, specific heat of water, T final minus T initial for the water, plus, and I'm just going to put yada, 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 yada. Okay, and if you just put in all the values that you're given, what should fall out of it, I believe, is the mass of the aluminum. I think will be the only unknown in there. You should be able to get all the T final minus T initials because the T final is given in the problem, right? So that thing's given, and all the initial temperatures are given, all the masses are given. So it'll just end up being a big, long algebra problem. So that should get you through 13. Let me take a moment here and read 14. Let's see, so a car's going down the road. It's moving along with some speed v, and I'll bet you the kinetic energy is going to be important, so you might want to start by calculating that and get some numerical value. And when the car stops, what happens is a big chunk of that kinetic energy ends up turning into internal energy, heating up the rotors. Now, how much of it actually heats up the rotors is kind of impossible to tell. Did 80% go into the rotors or 50%? It'll probably say something like that in the problem. It says the brake shoe converts the car's kinetic energy to thermal energy. So basically what they're saying is to assume all of this energy goes towards the heating up the rotors. Now, I'm going to make, like, here's a picture of our rotor here, and there's 2 to 4 depending on the brake system. I'm just going to draw one. That's really all we need here. And what we'll do is we'll use the total. You want the total mass there. And then, all right, we're going to have a heat transfer equal to mc delta T. You're going to use the kinetic energy for the heat transfer, assuming all goes in. Mass given in the problem. Rotors are made of iron, and you can calculate the temperature difference. That should roll you through that one. Let's chat about, let's see, 15. A cylinder contains some gas. The cylinder has a movable piston on top. All right, so as usual, let's start this with a picture. And so I'm going to do this kind of quick. There's the inside of my piston cylinder. Here's the movable piston. It has a weight on top. I think I saw, let me read that again. Let's see, cylinder has a movable piston on top, free to slide up and down. Pressure is kept constant. The piston is 8,000 grams. Okay, so no weight. Put a little thing on the piston there. But we do know the mass of this. Now, this thing's free to move. If we draw a free body of this object, you've got a gravitational force down due to its weight with the mass given. And the reason it doesn't fall is because of the pressure in the container. So this pressure's got a bunch of molecules in it, creating a pressure and hence an upward force up, which is equal to pressure times area. Now, even if the piston's moving, as long as it's moving slowly, the net force is 0. That's going to allow you to write a force equation and relate these two things. Let's see, find the work done on the gas if the temperature is raised a certain amount. Okay, so the pressure, what you're going to be able to get from this force equation is the pressure. That's going to be a known value. And then for the ideal gas, right, PV equals nRT. The pressure is a known value. The N is a known value. The R is a constant. You're given a bottom temperature here. Mine says 15 degrees. Yours is probably a different value. Don't forget to convert it to kelvins. And what that's going to allow you to do is calculate a V1. Then put in the second temperature and calculate the V2. And then you're going to know the change in volume. Now, hopefully, if you've watched my video series on how to calculate work done on a gas, all right, you look at the PV diagram, pressure against volume. We're starting at a V1 known number and a given pressure. And then as the temperature goes up, you're going to get a larger volume here. So on our PV diagram, it looks like this to volume 2. And that area there is going to give you the work done. You can also just do pressure times change in volume. So yeah, quite a bit of that to work through. All right, let me chat about 16 here. I've got to scroll this down a little bit. Oh my goodness, whole lot going on in 16. Okay, definitely what I'm going to want to do is cut and paste that problem here. So, need a picture here. I think in my picture we cut off a few things, but let me get this pasted here. And scale down. All right, I think there's more pictures here below, but All right, so let's start chatting about how to work these problems. So let's see, a sample of gas, right, at a given volume. Now, in case you're wondering, there's 1,000 liters is equal to 1 cubic meter. Probably need that because you want volume in cubic meters for the ideal gas law. Okay, cycle means like on this picture, when you do something like this and you end where you start, that's a complete cycle. Work done by the gas on the environment during each stage described below. Okay. All right, so we're going from 1 to 6 liters at constant pressure. So what I'm going to do is I'm actually going to sketch the PV diagram for that. So we're going from 1 to 6 liters at constant pressure. So the work is equal to this area here. Now, there's going to be a plus and minus sign we have to consider. I always talk about work done on the system. And when a gas is compressed, that's positive. When a gas expands, that's negative. But I suspect the homework here might be doing work done by the system. The way to check that is, you know, again, in my sign convention, I would call that work term positive. I'm sorry, whoops, I would call that work term negative. Because expanding gases are cooling, and hence their energy is going down and they're doing work on the environment. But the other sign convention is work done by the gas, in which case this would be considered positive. I suspect the book is going to call that a positive work term. Right here, probably plus. Okay, second, gas is cooled at constant volume. All right, so in my PV diagram, boy, I wish I would have started higher, but I'll just do a small rectangle here. Okay, it's cooling at constant volume. We're going straight down. Now remember, for a gas, work is pressure times change in volume. If you're going at constant volume, there is no change in volume. So I don't want to give you the answer, but that should be pretty close, or it should give you a pretty good idea. Until we're at a new pressure. So the second pressure is given now. The gas is then compressed. So in my PV diagram, we're going this way now. And then this area is going to give us the new work term. Right now we're compressing the gas. So by the way, if it accepts a plus sign for the answer of this one, it's going to be looking for a minus sign for this one. And then heated until its pressures increase. So in my picture, we're going up here. And again, there's no change in volume. That'll give you an idea for this. The net work done by the gas is the area bound on the PV curve. I'm going to do that in green. It's going to look kind of like this. So that is probably the crummiest PV diagram I have ever done, but probably good enough. So, you know, for part F, you're looking for which of these is closest to this, basically. Okay. Anyway, that should get you through that one. If you need more help, just ask. Happy to make another one. And have a great day.